day third years. In this video, we will discuss Lecture 3B, which is all about the properties of solutions, particularly the effect of composition on different thermodynamic properties, such as boiling and freezing points. In this lecture, you will be able to understand the variation of thermodynamic properties between an ideal solution and a regular or real solution. You will also be able to determine the changes in boiling and freezing points of a solvent due to the addition of solute. Furthermore, you will learn how to evaluate the osmotic pressure of a given solution. In the first part of this lecture, we will talk about how the thermodynamic properties differ with the type of liquid mixtures. First, ideal solutions. We have briefly mentioned ideal solutions in some of our examples in the previous lecture, and recall that it is assumed that the equations we got for perfect gases are also applicable to ideal solutions. In fact, calculation of thermodynamics of mixing for ideal solutions is the same as that of perfect gases. However, this does not mean that particles in ideal solutions behave the same way as perfect gases. In a perfect gas, there is no interaction between the molecules. In an ideal solution, there are interactions, but the average energy of the interactions in the pure liquids are just the same as that in the solution. Thus, the net change in energies when the liquids are mixed is practically zero. Recall the equations we got for perfect gases. The chemical potential of a substance J in the solution or mixture is given as the chemical potential of the pure substance J plus RT times ln of the mole fraction of J in the solution. The Gibbs energy of mixing is given by this equation. And similar to perfect gases, ideal solutions also mix spontaneously, given by the negative value of the Gibbs energy of mixing in any solution composition, as seen in the figure. Similarly, the entropy of mixing is obtained using negative delta G over T. As seen in the graph, the entropy of mixing of the solution is positive. The increase in entropy of the system acts as the driving force of the spontaneous mixing of the liquids. And since the interactions between the pure liquids and the particles in the solution are essentially the same, the change in enthalpy during mixing is also zero. To determine the change in volume on mixing, recall that the rate of change in Gibbs energy with respect to pressure at constant temperature is equal to volume. The ideal volume of mixing is then equal to the partial derivative of the Gibbs energy of mixing with respect to pressure at constant temperature. But since the Gibbs energy of mixing is independent of pressure, this expression becomes zero. Therefore, the change in volume during mixing is zero. However, for real or regular solutions, the interactions of molecules in the pure liquids and the solutions are all different. This therefore results to the enthalpy and volume changes during mixing. There may be cases as well that the Gibbs energy of mixing may be positive, which means that the liquids are immiscible and the separation of the mixture is spontaneous. For regular solutions, the entropy of mixing is the same for an ideal solution, but the enthalpy of mixing is non-zero. This can be understood as two kinds of molecules are randomly distributed the same way as in an ideal solution, but the energies of interactions are different with each other. Now, how do we quantify this deviation from ideality? The thermodynamic properties of real solutions are expressed in terms of excess functions Xe. And this is given by the difference between the observed thermodynamic function of mixing and the function for that of an ideal solution. The figures below show examples of the dependence of excess functions on composition. Remember that both the enthalpy and volume of mixing for ideal solutions are zero. Therefore, the excess enthalpy and volume are just equal to their observed values. As seen on the graphs, these are no longer zero. Recall that in a regular solution, the randomness of the molecules is the same as that in an ideal solution. This means that the excess entropy SE is zero. But the energies of interactions differ, with the excess enthalpy HE as non-zero. To quantify HE, we assume that it is dependent on composition and is given by the equation HE is equal to total moles times Xi RT times the mole fractions of A and B in the solution. Xi is a dimensionless parameter that represents the measure of the energy of interactions in the solution relative to interactions in the pure liquids. If this function is plotted as shown in this figure, it can be seen that it is similar to the plot of HE in the previous slide. As shown in this graph, if the parameter Xi is negative, HE and therefore the observed enthalpy of mixing is negative, which means that mixing is exothermic and the interactions in the mixture is more favorable than the interactions in the pure liquids. On the other hand, if Xi is positive, HE is positive, meaning mixing is endothermic and interactions in the pure liquids are more favorable. To determine the Gibbs energy of mixing for regular solutions, recall this expression. We know that the observed enthalpy of mixing is just equal to excess enthalpy HE and entropy is just the same as that in ideal solutions. Simplifying, we get this equation for Gibbs energy of mixing. As can be observed, it is similar in form to that of ideal solutions, but with the additional term for the Xi parameter. Now let us consider this example. Identify the value of the parameter Xi that would be appropriate to model a mixture of benzene and cyclohexane at 25 degrees Celsius and estimate the Gibbs energy of mixing for an equimolar mixture. We choose the maximum value of He in the figure, which is about 700 joules per mole at an equimolar composition. To solve for the parameter Xi, we use the expression for excess enthalpy. Since the given is molar enthalpy, we discard the total moles from the equation. Solving for Xi, we get 1.13. Then to calculate the molar Gibbs energy of mixing, we use the expression we got for real solutions. Take note that both sides were divided by n to get the molar quantity of the Gibbs energy of mixing. Substituting known values, we get negative 1017.5 joules per mole. The second part of this lecture focuses on the effect of composition on colligative properties of the solvent. A colligative property is a physical property that depends only on the relative number of the solute particles in the solution and not on its identity. Examples of colligative properties are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. The terms already give you an idea of the general effect of the number of solute particles on these thermodynamic properties. In this discussion, we will denote the solvent as A and the solute B. We will also set two assumptions, namely, the solute B is not volatile and does not dissolve in solid solvent A. This means that pure solvent A will be obtained in its gas and solid phase. Solute B remains dissolved in the liquid phase. All colligative properties result from the reduction of chemical potential of the liquid solvent due to the presence of the solute. As seen in this figure, the chemical potential of the pure liquid solvent is higher than that of the liquid solvent in the solution. The chemical potential of the solid and vapor forms of solvent A is unaffected because the solute is not present in these phases. The lowering of the liquid chemical potential results to the liquid-vapor equilibrium occurring at a higher temperature or the boiling point increases, and the solid-liquid equilibrium occurs at a lower temperature, thus decreasing the freezing point. The molecular origin of the decrease in chemical potential is essentially an entropy effect and not enthalpy, because even for ideal solutions where enthalpy of mixing is zero, the same phenomenon occurs. Addition of solute particles result to an increase in disorder of the solvent compared to the pure solvent. The increased randomness lowers the tendency of the liquid solvent to freeze and to vaporize, thus lowering the freezing point and increasing the boiling point respectively. Now let's discuss them one by one. To study the boiling point, we consider the equilibrium of the vapor solvent A with the solution of solvent A and solute B. Recall that for systems in equilibrium, the chemical potential of one substance should be equal in all phases of the system. Therefore, the chemical potential of solvent A in the vapor is the same as that in the liquid phase. Writing that in equation form, we get this. Note that from our previous lecture that the liquid chemical potential of a substance in a binary solution is equal to the chemical potential of the pure substance plus RT times ln of its mole fraction. Isolating ln XA, we get this expression, where the difference of the chemical potentials of the pure vapor A and pure liquid A is just equal to the molar Gibbs energy of vaporization of the pure solvent A. If we take the derivative of both sides with respect to temperature, we get dln XA over dt is equal to 1 over R times the derivative of delta G of vaporization over T with respect to temperature. Recall from Module 1 that this derivative term is just equal to negative delta H over T squared based on the Gibbs-Helmholtz equation. To evaluate the previous expression, we multiply both sides by dt and integrate from ln XA is equal to 0, or when XA is equal to 1 and boiling point is equal to T star, up to ln XA when boiling point is some temperature T. Integrating, we get ln XA, which is also equal to ln 1 minus XB for binary mixtures, equal to negative enthalpy of vaporization divided by R times the quantity 1 over T minus 1 over T star. Again, T star is the boiling point of the pure solvent A and T is the boiling point of solvent A in the solution. Now, if we suppose that the amount of solute is very small, we can approximate ln 1 minus XB as negative XB. And because the increase in boiling point is small, we can also assume that T is approximately equal to T star. The term 1 over T minus 1 over T star then becomes T minus T star or delta TB divided by T star squared. Delta TB pertains to the change in boiling point or boiling point elevation. Now, incorporating these approximations in the previous equation, we get XB is equal to enthalpy of vaporization divided by R times delta TB over T star squared. Isolating delta TB and combining all constant parameters in a single empirical constant, we get the expression delta TB is equal to KXB, where K is the boiling point elevation constant and is equal to RT star squared divided by enthalpy of vaporization. Since the mole fraction XB is directly proportional to its molality B, the boiling point elevation equation can also be expressed in terms of molality as delta TB is equal to KB times B. KB is the empirical molal boiling point constant wherein its value for different substances are already known. Several references can be used to obtain the values for the molal boiling point constant and, as you will see in the succeeding slides, the molal freezing point constant Kf. Note that these constants are used using the expression with molality and not mole fraction, as expressed in the units of Kb and Kf as Kelvin kilogram per mole. For freezing point determination, we focus our interest on the solid-liquid equilibrium of solvent A. Using the same analogy we used for boiling point elevation, we get the change in freezing point or the freezing point depression. Delta TF is equal to K prime XB, where K prime is equal to RT star squared divided by the enthalpy of fusion. Note that T star is the freezing point of the pure solvent and delta TF is equal to T star minus T. Expressing in terms of molality, we use the equation delta TF equal to Kf times B, where Kf is the molal freezing point constant. As mentioned in the discussion for boiling point elevation, the increase in entropy due to the presence of solute causes the weaker tendency of the solvent to form the vapor. More than resulting to an increase in boiling point, this also leads to the decrease in vapor pressure. The vapor pressure lowering is expressed by Rayleig's law for ideal solutions. For ideal dilute solution, the partial pressure of the solute is calculated using Henry's law, while that of the ideal solvent is obtained using Rayleig's law. The last colligative property that we will discuss is osmotic pressure. But first, let's define osmosis. This is the spontaneous passage of a pure solvent into a solution separated by a semi-permeable membrane that allows only the passage of the solvent and not the solute. Consider the figure below, wherein one side contains the pure solvent and the other is a solvent-solute mixture, which is separated by a semi-permeable membrane. Because of the concentration difference, the pure solvent tends to flow towards the side of the solution to dilute it and somehow equalize the concentration. This results to a change in height on the side of the solution, and this height difference is proportional to what we call the osmotic pressure. However, the thermodynamics of this arrangement is complicated to address because of the change in concentration of the solution as the solvent flows towards it. Instead, we can look at osmotic pressure, represented by the capital Greek letter pi, as the pressure that must be applied to the solution to stop the influx of solvent. This arrangement is simpler since there is no flow of solvent and the solution concentration remains unchanged. The thermodynamic treatment of osmotic pressure is based on the notion that at equilibrium, the chemical potential of the solvent must be the same for both sides of the compartment as shown in the figure and in this equation. It is known that the solute lowers the chemical potential of the solvent, but this decrease is restored to its pure value by the application of pressure. We know that the chemical potential of the solvent in the solution can be expressed as the chemical potential of the pure solvent in the same pressure plus RT ln XA. Combining the two equations, we get the chemical potential of the pure solvent at the increased pressure minus the chemical potential of the pure solvent at its initial pressure is equal to negative RT ln XA. Recalling the variation of Gibbs free energy with pressure discussed in Module 1, we know that the change in molar Gibbs energy, or the final molar Gibbs energy minus initial molar Gibbs energy, is equal to the integral of molar volume times dP evaluated from initial to final pressure. And since molar Gibbs energy is equal to chemical potential, we can also express this equation as follows. The final chemical potential at the increased pressure minus the initial chemical potential at the original pressure is equal to the integral of the molar volume times dP evaluated from the initial pressure to the increased pressure. Knowing that the change in chemical potential is equal to negative RT ln XA, we substitute that to get this equation. We evaluate the right-hand side of the equation by assuming that the change in pressure is small, that the molar volume is unaffected or remains constant. We therefore get molar volume times the osmotic pressure. For very dilute solutions, We can again approximate ln xa as negative xb, same as what we did in the derivation of the boiling point elevation. Our equation then becomes RTXB is equal to molar volume times the osmotic pressure. Noting that since we assume that XB is very small for dilute solutions, we can also approximate XB as equal to moles of B over moles of A. Recall also that the total volume can be obtained by getting the product of moles A and molar volume. The equation then becomes RT times the moles of B is equal to volume of the solution times osmotic pressure. You may observe that this equation is similar in form as that of the ideal gas equation. Isolating the osmotic pressure pi and defining that moles of B divided by the solution volume is just equal to its molarity, we get the equation for osmotic pressure equal to the molar concentration of B times RT, and this relation is called the Van Hoff equation and is valid only for ideal solutions. Let's consider this example. The addition of 5 grams of a compound to 250 grams of naphthalene lowered the freezing point of the solvent by 0.780 Kelvin. Calculate the molar mass of the compound. Given here is the molar freezing point constant, 6.94 Kelvin kilograms per mole. To solve this problem, let us analyze the equations that we will need. The molar mass of the solute is given as mass of the compound divided by the moles of the compound. The moles of the compound is calculated from its molality times the mass of the solvent. And from the freezing point depression equation, the molality is given by delta Tf divided by Kf. Therefore, the molar mass of the compound can be calculated by combining these expressions and is given by mass of the compound times Kf divided by the mass of the solvent times delta Tf. Substituting known values, we get 177.95 grams per mole. This ends Lecture 3B. Thank you for listening and see you in our next synchronous discussion.